Welcome to Gooseberry Science and Education videos. My name is Jo. Today, we have an absolutely fascinating explainer lined up for you. And to help me guide you through the data, I want to introduce my little orange assistant, Gooseberry. Give everybody a wave, Gooseberry. Together, we're going to explore the absolute cutting edge of biochemical sensing. We are taking a wild journey across scales today, from microscopic wearable tech that sits right on your skin, all the way up to macro-scale sensors monitoring the health of entire cities and the very depths of our oceans. Okay. Let's dive right in and see how the technology tracking our individual health is evolving to track the whole world around us.
Section 1. The Broken Promise. To really understand where we're going, we first have to grasp the foundational challenge here. And honestly, it's a story of a broken promise when it comes to long-term autonomous sensors. Think about this. It has been over 40 years since scientists first proposed the idea of an artificial pancreas, a device that would seamlessly combine continuous glucose monitoring with an automated insulin pump. Yet, despite decades of research and literally billions of dollars in investment, medical implants still face massive hurdles. They often fail after just a few days inside the body. As research by Dermot Diamond highlights, that vision of highly reliable, affordable sensors functioning autonomously for years, it just remains unrealized. Because our bodies naturally fight off foreign objects, the overwhelmingly dominant paradigm in health diagnostics today is still heavily reliant on single-use disposable sensors. We just haven't cracked the code for long-term internal implants yet.
Section 2. Wearable health trackers. So, since putting sensors permanently inside the body is so incredibly difficult, science has cleverly pivoted. If we can't reliably go inside, why not gather the data from the outside? We're now looking at a wild variety of testable biofluids. Gooseberry, point these out for us. We can test sweat, tears, saliva, exhaled breath, and interstitial fluid, which, if you didn't know, is just the fluid found in the spaces right around your cells. Think about what this actually means for us. We can harvest incredibly rich diagnostic data without needing a single painful blood draw. No needles, no trauma, just a simple patch or even a smart contact lens quietly collecting fluids that our bodies are naturally excreting all the time anyway.
So what exactly are we looking for in these fluids? Well, we're tracking key metabolites. Metabolites are the direct products of our cellular metabolic processes, and their concentrations change dynamically, in real time. For instance, continuous glucose monitoring from interstitial fluid or sweat is completely revolutionizing diabetes management as we speak. Meanwhile, tracking lactate levels in your sweat can give us immediate, real-time indicators of muscle fatigue, hypoxia, or even severe conditions like sepsis. These non-invasive patches give us a continuous, live dashboard of our physical condition.
Section 3. The microfluidic revolution.
Now, you might be wondering, how on earth does a tiny patch process a microscopic drop of sweat or a single tear? The secret sauce here is microfluidics, the precise control and manipulation of fluids constrained to a really small, typically sub-millimeter scale. Gooseberry, can you trace that path for us? Imagine tiny microscopic channels engineered so perfectly that they use natural capillary forces and surface wettability to transport fluid. It happens completely automatically. The fluid is routed right into the sensing module of the wearable device without needing any external power or bulky mechanical pumps. It is passive, intelligent design at a microscopic level. But here's the catch. These microscopic channels can't be made of rigid, brittle materials if they're going to be worn on a constantly moving human body. Instead, they rely on advanced, flexible substrates to power these wearable biosensors. We're talking about incredibly biocompatible materials, like PDMS, which is a type of flexible silicone, as well as specialized textiles, paper, and hydrogels. These materials allow the sensors to be worn comfortably right on your skin, bending and stretching perfectly as you move. And this flexibility is absolutely crucial because it resists motion-induced errors and keeps those delicate microfluidic channels perfectly intact while you go about your day. Section 4. Monitoring whole cities. Okay, so we've looked at the microscale, where sensors track an individual's sweat or tears. But what happens if we scale this entire concept up and apply these exact same principles to an entire city? It's a massive challenge, but look at how researchers are tackling it through this data processing pipeline. Instead of a patch on your arm, scientists are placing biofunctionalized fiber optic sensors directly into public sewage networks. This allows for continuous, real-time, label-free tracking of emerging pathogens. Specifically, this system was designed to detect SARS-CoV-2 antibodies. The sensor reads optical interference signals directly from the raw, complex matrix of city wastewater. It basically acts as an early warning system for potential infectious outbreaks across entire communities.
Section 5. AI upgrades sensing.
But as you can probably guess, there is a huge catch. City sewage is incredibly messy. It's a highly complex, noisy environment, which makes simple optical data detection a massive headache. Simple detection rules just do not work when there's that much background interference. To rescue this data and make these sensors actually usable, researchers brought in artificial intelligence. And guys, the results are staggering. When using traditional single threshold monitoring, which is basically just setting a rule that says if the signal hits this specific peak, trigger an alert, the accuracy was a terrible 38.9%. It was essentially failing to read the noisy sewage data correctly. But when they applied machine learning models to analyze the exact same optical signals, looking at comprehensive global statistics and morphological features of the data, the balanced accuracy skyrocketed to 92.9%.
And this comparison brilliantly illustrates the difference. When you look at the results for the traditional threshold method, out of the positive samples, it missed a whopping 53 positive cases. Those are false negatives. It was basically blind to the pathogen. Now compare that to the nearest neighbor's classifier machine learning model. Out of a similar set, this AI model only missed 2 positive cases. 2! That is a triumphant data story right there. By pairing physical fiber optic sensors with machine learning algorithms, we can confidently and accurately read data in literally the most chaotic environments imaginable.
Section 6, the autonomous future. So where is all of this heading? By merging the advanced, flexible materials we use in microwearables with the powerful machine learning algorithms we use for citywide monitoring, the future of sensing is going to mimic nature itself. To survive for years in remote locations without any human intervention, next-generation sensors are being designed with 3D biomimetic building blocks. This means they'll have switchable properties, the ability to self-diagnose their own physical condition, and even self-repair capabilities. They'll also be designed with anti-fouling materials so they don't get all clogged up by biological matter over time. Honestly, they are going to act almost like living organisms in their resilience. To give you a final, truly awe-inspiring example of what this looks like on a global scale, consider these autonomous underwater vehicles, or AUVs, equipped with novel sensors to track ocean carbon and alkalinity. These devices can travel long ranges into the deep ocean, independently taking complex biochemical measurements for extended periods of time. It proves just how massive the reach of this technology has become, surviving in extreme remote environments to give us absolutely critical data about our planet's climate. Which leaves us with this final, provocative thought. As machine learning and biomimetic materials finally allow sensors to survive autonomously for years, where are they going to go next? Will they primarily explore the uncharted depths of our oceans, or will we finally fulfill that 40-year-old promise and place them permanently and safely inside our own bodies? It's an incredible frontier. Thank you for joining Gooseberry and me today. Please like and subscribe if you enjoy the content. We are already working on a new topic.